This is Catherine Nightingale at Chattanooga State Community College, and this video is for Linear Algebra section 6.2 on the topic of orthogonal projection of a vector onto a line. Let's start with the requirements that we have for this section, and that is that L, the line, has to be through the origin so that we can think of it as the span of some vector u. So remember, a span always has to include the zero vector. And so let's draw our line through the origin. This is an example in R2 because that's the easiest one to draw by hand. So we have L through the origin, and then we have this vector u on L, and we can think of L as the span of u because you just multiply u by any scalar to get to different points on L. Okay, now that we have our requirement, let's go to the actual orthogonal projection section. So the key idea of the section is that we're going to decompose vector y into the sum of two vectors, one being the shadow. I put that in quotation marks because it's not technically called the shadow, it's called the projection, but it's the shadow of y on line L, and the other vector is going to be orthogonal to our line L. Now the shadow of y on the line is called the orthogonal projection of y onto L, and it's denoted y hat or proj subscript L y. So the projection of y onto L is how that is said out loud. Here's a picture of an orthogonal projection. You can see you have this vector y and the line L, that's the blue line. And basically what you do is you just drop y down onto the line. So you drop it straight down from where it is, and what happens is it creates a 90-degree angle with your line. So y hat is not going to have the same length as y. It's going to be the point that you would get to by dropping that point at the end of y just straight down onto your line. Now since L is through the origin, we have this vector u, and we can think of L as the span of u. And then we also have this portion which we call z, which is y minus y hat, that is actually orthogonal to L, so it creates a 90-degree angle. And then we have the actual orthogonal projection, y hat, is on the line. So when we talk about the projection, we're talking about projecting down onto the line, and it's actually sitting on that line. And then z is the part that's orthogonal. So there's your visual of the orthogonal projection in R2. Okay, let's talk about finding y hat, or your orthogonal projection. I broke it down into 6 steps. First of all, we want to write y, our original vector, our given vector, as y hat plus z, where y hat is on the line and z is perpendicular to the line. Y hat is called the orthogonal projection. Since L is through the origin, it's equivalent to the span of u for some vector u. And therefore, since y hat is on L, we can write it as a scalar times u. Since L is the span of u, any point on L is just some scalar times u. So we have y hat equals alpha times u. Now what I'm going to do on the next slide is combine steps 1 and 3, and I'm going to substitute the alpha u in for y hat. into the equation in line 1. Okay, so from lines 1 and 3, we have now that our original vector y is equal to alpha u plus z for some scalar alpha. And that should be an arrow over the u, not a hat. So I substituted in the alpha u for the y hat. Now, since u and z are perpendicular, we can use theorem 5 to find the scalar alpha. So we have alpha equals y dot u over u dot u. So y hat is equal to y dot u over u dot u times u. So that's scalar times u. So this is basically the formula you need to know in order to find y hat. Step 6, now that we have the orthogonal projection, we know that y equals y hat plus z, so we can solve for z and we get z equals y minus y hat. So these two equations for y hat and for z are the two that you really need to write down and remember. Okay, one practice problem. Compute the orthogonal projection of the vector 2, negative 1 onto the line through negative 1, 3 and the origin. So it's good, it goes through the origin. Let's get a little visual of what's going on. So I'll put my axes there on my grid. These are in R2, so they'll be easy to draw. I have my vector 2, negative 1, and then I have my point negative 1, 3, and the origin. I'm going to make a line through those. Now what I'm going to do is I'm going to drop down y onto the line. So I'm going to call my vector 2, negative 1 vector y. I drop it down orthogonally onto the line, and I'm going to call that vector z. Now this vector from the origin to the point where z hits the line is my orthogonal projection y hat. Okay, now I have the formula y hat equals y dot u over u dot u times u. So I'm just going to go ahead, here's my y, here's my u. I'm going to go ahead and do the dot products. So y hat equals 2 times negative 1 plus negative 1 times 3 over u dot u times u. So I plug in all the numbers, and now I just simplify. That's negative 5/10 or negative 1/2 if you simplify, times my vector. Multiply and simplify, I get 1/2 negative 3/2. And you can see that that's exactly where the tip of y hat is in the picture. Okay, so there's my orthogonal projection. That's all there was to it. I do want to go ahead and talk about what you would do if you wanted to find z as well. So we've finished the practice problem. We found the orthogonal projection. But now we have the orthogonal projection of y onto the line through negative 1, 3 and the origin. And it's 1/2 negative 3/2. Now, if we wanted to find z, the part perpendicular to L, we could use the formula z equals y minus y hat. And so if we do that, we just plug in the y we were given was 2, negative 1. The y hat we found was 1/2 negative 3/2. Just do your subtraction and you get 3/2, 1/2. So this particular vector is perpendicular to the line L. Okay, let's do just a quick visual of what it looks like. You have your line, you have your vector y, you have your orthogonal projection y hat in yellow, and then you have your z, which is perpendicular to the line at 3/2, 1/2. And you can see, since in physics you can move vectors around in space as long as you preserve direction and length, we could put z to connect the tip of y and y hat and form our right triangle. So that's how you do orthogonal projections, is just using those formulas. Using these formulas for y hat and for z, I flipped back to a previous slide where we had them written. So y hat equals y dot u over u dot u times u, and z equals y minus y hat. And that's what we did in our example to find those.